Hi, welcome back to this class, Thermodynamics. In our basic education, we learn about the basic phases of matter. We know of solid, liquid, and gas. And these phases of matter can have its physical changes or phase transitions or phase changes. A liquid material could change into solid or into gas. And in the process of changing its phases or states, for example, we have a liquid which will be evaporized through boiling usually, then it will become a gas. And from the gas stage or gas phase, when this gas substance would condense, then it will go back to its liquid form. And if we have a solid material which changes its state or phase directly into liquid, then we call this as fusion. And the reverse process of that would be solidification or crystallization. And for the changes of phases between the solid and gas, where we can change the gas into a solid directly, we call that deposition. And for the change of solid back to its gaseous phase, we call that sublimation. Again, in this part of your course, we are talking about the thermal properties of matter, and this topic will be discussing phases of matter. Our previous knowledge about the phases of matter, we easily identify the three phases of matter, the solid, liquid, and the gas. However, for a more complex situation, we can better understand these phases of matter or transition from one phase to the other when we study about the phase diagrams. This phase diagram shows us the relationship between the pressure, the volume, and the temperature, which would dictate the changes of phases or state of this matter. First, we will consider the pressure, temperature phase diagram. The assumption of which is, under this diagram, the volume of the material or matter is set to be fixed or at constant value. This is the most common pressure temperature diagram, which would allow us to understand the relationship between the phases of matter through the identification of its curves. On the horizontal axis, we have the axis for temperature, and for the vertical axis, we have the axis for the pressure. And we identify different phases of matter here to be under this light brown area. The materials are said to be solid, and here in the bluish white area, it is said that the materials are all liquid, and below that, it is said that the materials are all vapor. And there is this very important curves which signifies the relationship between the values of pressure and the values of temperature, at which these phases would coexist. This is the boundary values for pressure and temperature. For these processes would occur or would be experienced by a certain material. We have here this line, this one. This represents the fusion curve. At these values of temperature and pressure, the state or the phase of matter coexists in a state of solid and liquid. Every values of temperature with a corresponding value of pressure, if a solid material is subjected to this certain value of, for example, at PA. At a certain value of PA, a solid material is subjected to a temperature somewhere between TD and TB. As long as it satisfies the condition for the fusion curve, it is said that at that specific pressure and temperature, there exists both the solid and the liquid form or phase of this kind of material. And the same with the vaporization curve. For the vaporization curve, at a certain value of pressure, for example, at this value of pressure, and which is satisfying also the value of temperature at this horizontal axis, then at this point of pressure and temperature, there exists both the liquid and the vapor state of this kind of liquid material. And so with the sublimation curve, again with the same principle. For example, at this specific pressure at PS and at this specific temperature TD, then it is said that at this specific point, there exists both the solid and the vapor state of this material. Other than the sublimation curve, fusion curve, and vaporization curve, there are two important aspects in considering a phase diagram. First, we'll discuss about the critical point. The critical point is said to be a point where the material properties changes smoothly and with change in pressure or temperature, rather than undergoing a phase change. At this particular point, the boundary between the liquid and the vapor vanishes. That means there is only one phase that exists, and this is neither a pure liquid or pure vapor. This point, the critical point, the only phase that exists is a combination of a liquid and a vapor. For example, let us consider a water. Water at its critical point, there is a different characteristic that will be exhibited. At normal or at room temperature, we know that water is a good conductor, water is a good solvent, water is a good carrier of electrolyte. However, at its critical point, everything changes. At critical point, water will be a bad electrolyte carrier, water will be a bad conductor, and at that specific phase where the liquid and the vapor phase of the water coexist, a water molecule would prefer attaching to a non-polar gas or to a organic molecule, and that is not exhibited by water at any other phase. Either it's a form pure liquid or a pure vapor or a solid form of water. That is only present, that is only exhibited at a certain critical point. That is at a specific fixed amount of pressure and temperature to determine the critical point of water. Though it goes beyond the discussion of our course, but the phases of matter does not limit only on the solid, liquid, and the vapor or the gas phase. There is this what we call the supercritical fluid, which is a fluid which goes beyond the value of the critical point. When a material or a matter goes into this supercritical fluid form, it can no longer be solidified using pressure. And for gases which goes beyond the value of the critical temperature, it can no longer be liquefied using pressure only. And that goes beyond the coverage of our discussion. Another point which is very important for us to understand the characteristic or the phase changes of a matter is the tripole point. A tripole point is a point in which the pressure, and the temperature gives a certain state or condition that will allow the existence of both the solid, the liquid, and the gas. And that is why the term itself tells us this is the tripole point. An example of this is this video clip where in a fixed volume, there exists both the liquid water, the ice, which is the solid form of water, and of course the bubbles, which exhibits the presence of water vapor. This is a condition where the three phases is observed in this particular video clip. For a long period of time, it has been accepted that the presence of the tripole point of water has been used as the base unit for the Kelvin scale. Though recently the standard or the base unit of the Kelvin scale has been considered in some other form, because the consideration or the definition of this tripole of the Kelvin scale using the tripole point of water, it was just used by definition and not by calculation or experimental discoveries. So for all we know, we define the base unit for the temperature scale of Kelvin to be at 273.1516 Kelvin, or that's roughly to 273.16 Kelvin, or that is 0 degree Celsius or 0.01 degree Celsius. There are other factors that we need to understand for the possible changes of matter. From the 3D phase diagram, we have here the 3D phase diagram where the pressure and the volume and the temperature are all present. And the PV and the PT diagram, which I have shown in the previous slide, is a projection in this plane where we discuss about the critical point and the tripole point of a matter. Except water, which is anomalous, because most materials will exhibit expansion as it melts. However, the water, as it melts at this temperature range from 0 to 4 degrees Celsius, as it melts, it contracts. And that's a unique property of a water. Remember that in section 1.4, we discussed about thermal expansion of solid, where when you introduce a certain amount of temperature into a solid, considering its thermal expansion coefficient, may it be linear or volume or surface expansion, then when we introduce a certain amount of heat or change in temperature, there will be an expansion. And if we are to remove a certain amount of heat or just lower the temperature of that material, it will exhibit contraction or compression. When we look at the pressure volume diagram, we can see that for a certain material at constant temperature, the assumption here is that the material would change its phase at constant temperature. So this might come complicated, but I would like to emphasize this portion of the PV diagram, where we are used to hearing in our basic education about isotherms, about isothermal process. This curve here is somewhat like similar to isotherm, where at this specific condition, the gas or the material would change its phase at constant temperature. And at this particular condition, we can see that this is at the tripole point. At that specific temperature and that specific pressure and that specific volume, there exists both the solid, the liquid, and the gas. Similar to our pressure temperature diagram, where at this specific fixed value of volume and that particular amount of pressure and that particular amount of temperature, there exists both the solid, the liquid, and the gas phases of this particular matter. So this PVT surface diagram, this represents a behavior of a material that expands as it melts. So again, the two-dimensional diagrams presented here, the PT phase diagram, this one, and the PV phase diagram, this one, represents the projection of these PVT surfaces for a melting material. So thank you for listening, and that ends our discussion on the thermal properties of matter.